Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
We have some deep issues to address today in only 50 minutes. But a theme through today is going to be that of serendipity, that of happy accidents. And so I'm starting today with an image in the background of my title slide here, with a collection of galaxies imaged by the Hubble Space Telescope. And I suspect there's some astronomy lowbrow folks in the audience who know the name of this little group of galaxies. Anybody know? It's not Stephan's sextet, it's Seyfert's sextet. You're close. Now, how do you know? I mean, this is a Hubble Space Telescope image, and the Hubble Space Telescope is, of course, peering out into space. And what it does really well is to peer out into deep space. So how do you know those galaxies are actually together spatially in 3 dimensions? 2 dimensions, yes. But what about 3 dimensions? Because when you look at this image, you see other things. And in fact, you see things like little red blobs, here, here, here. Those red blobs are other galaxies, and they're more distant. You can tell that they're more distant just from looking at the image, because they're smaller in an angular sense. They're smaller, subtend a smaller solid angle, and they're redder. And the red nature is due to the expansion of the universe. Their light left them when the universe was much younger. And as the universe expands, the photons of light that are traveling toward us expand with the universe. And so they stretch to redder and redder wavelengths. And so that's why these background systems appear red compared to the foreground systems. Well, it turns out that Seifert could count correctly. There are 6 blobs. But he was wrong in the sense that one of these galaxies is not at the same redshift as the others. And redshift is a measure of distance in astronomy, right? And if I asked you, I could have a clicker question which would be devious. And my students who have come today, some of whom are sitting in the front row, will tell you I don't like devious questions. I mean, I like hard questions, but not devious ones. So it turns out that if I asked you the question, which one do you think doesn't belong? The color image isn't so great here, but you can tell that the color of this galaxy is a little different. So you probably would have chosen that one. But the answer is actually this one. That face-on spiral galaxy is 5 times more distant than the rest of the quintet. And in fact, it's even more interesting than that. This galaxy itself is not really its own galaxy. It's a piece of this galaxy that got thrown off as these 2 galaxies are interacting. So it's a tail, it's a tidal tail, as we call it in astronomy, from that parent system. And so Seyfert's sextet is really Seyfert's quartet. All right, well, what about the title? What about this word adventitious? It is the beauty of the internet, of course, that you can go to dictionary.com or thesaurus.com and look for synonyms. And I was looking for a synonym of accidental, because I didn't want to title this the accidental universe, this talk, the accidental universe, because accidents tend to be bad, although there are sometimes happy accidents, right? So adventitious seems a sort of neutral word. And, most of you, except those who do crossword puzzles religiously, probably haven't, you don't use it in everyday speech. What does it mean? Well, you go to the Oxford English Dictionary, which is, I hold that in high esteem. The meaning of the nature of an addition from without, extrinsically added, not essentially inherent, supervenient, accidental, casual. Okay? It was the word of the day on October 9th of 2002. And here, and again, the beauty of the internet, and here is a usage in biology. The trunk spores are actually adventitious roots that have erupted from the trunk in response to some stress or injury to the inner bark and are probably no reason for concern. So did our universe appear spontaneously, and is it no reason for concern? That's kind of what I'm trying to address today. Right, so now you have your clickers. It is time for your first question. The sense of scale is important to address the cosmos. So my question to you is, the universe has a finite age. Photons travel at a finite speed, so there's a finite size that we can address observationally. That's what I want to call the visible universe, and that's why I underline visible there. What is the ratio of the size of the visible universe to the size of our galaxy, our home Milky Way galaxy? Okay? And let me remind you about powers of 10. So this would be that the universe is the same size. 10 to the 0 is 1. 10 to the 3 is 1,000. 10 to the 6 is a million. 10 to the 12 is a million millions, right? So let's collect your answers. Emily is happily doing that. And there is a correct answer here that I will. So the idea here is that if you lined up Milky Ways, how many, and they stretched across the visible universe, how many Milky Ways would you have to line up? Okay, so well, look at that. There's an answer distribution which is kind of peaked between D and E. And D and E were very big numbers, 10 to the 12th and 10 to the 20th. Emily, you want to flip back? Because the correct answer, it turns out, is a million. It's only a million galaxies long. You know, that's kind of small. So, okay. And let me point out that if you want to get a big number, then what you do is you take the size of the universe to the size of the Earth, okay? That's 10 to the 20. And that shows you how much smaller the Earth is compared to the galaxy, relative to the galaxy in the universe. Right? We're much more condensed inside our galaxy than the galaxy is within the visible universe as a whole. One more question. What about time? What is the ratio of the age of the universe? And here's where I think that many of you pros, many of you pros will know the answer here. And here, you want to consider yourself, this is order of magnitude physics, right? So if you can either think of yourself as 10 years old or 100 years old in this context. And I'm going to choose 100, okay? Because I think logarithmically, and logarithmically I'm closer to 100 than 10. Although emotionally, I'll stop there, okay? Great, so let's see what your answer is. Okay, the most popular answer is D. And you're going to flip back? And that indeed is the correct answer. Well done. I knew you guys could pull it off. Because, okay, I'm 100 years old. Everybody in this room is close to 100 years old in a logarithmic sense. And the universe is 10 billion years old, 14.7 billion years old. And that's 10 to the power 10, because a billion is 10 to the 9, 10 billion is 10 to the power 10. 10 to the 10 divided by 10 to the 2 is 10 minus 2 is 8, right? Excellent. All right, now that's the end of the quizzes for now. I have one more question later on in the talk here, but let's now, instead of asking a question, let's have a little fly-through of the local universe. So here we're starting from our Milky Way. We're starting from the solar system and we're going out. And this movie has been put together by folks at the University of Hawaii, Brent Tully in particular. We're flying out through a nebular gas cloud where stars are forming. And we're going to be lifting out in a few moments outside of our galaxy and looking back. So the Milky Way galaxy is a spiral galaxy. It has most of its stars in a disk that spiral around a common center, although there's a bulge. So here's the galactic center down here, and you can see that in the sky. Although I'm not an astronomer, so I'm not sure at what time of year it's in the sky. I apologize, but it is up there on occasion. I'm sorry. So here's the center of our Milky Way. We're lifting out of the disk now, and we're just going to I'm going to show you two movies. The first movie, we're going to fly out to the nearest large structure, the nearest large cluster of galaxies, known as the Virgo cluster. And then in the next movie, we're going to lift out even farther than that. And in fact, we're going to lift out to the size scale of the entire visible universe. But here we leave our Milky Way behind, and we fly out and turn around. And we'll see there's a small collection of galaxies surrounding us that's part of the local group. There is Andromeda, our nearest large neighbor, and its neighbor, which we'll fly through soon. And then we'll turn our attention to heading to the Virgo cluster. And so within galaxies, you see these regions of gas that are forming stars. And when stars die, they blow out supernova, and they create those holes that you're seeing in the gas distribution. And there's the core of the Virgo cluster there, and notice that the distribution of galaxies is not entirely random. This is what's really out there. I must remind you that this is data based on actual telescopic observations. This is not just a made-for-TV movie of the local universe. This is the real thing, with real images of the galaxies involved. And so there's this great cluster down here, and when we zoom in, we're going to find We're going to follow essentially this little highway. This is a collection of galaxies lying along what we call a filament. And we'll zoom in along that filament. And over time, this is what the action of gravity does. It makes material flow to dense regions. And that's what's happening. This cluster is being built through gravity, gravitational amplification of some initial fluctuations that we'll talk about further in a few minutes. And then at the core of this cluster, there's a very large elliptical galaxy known as M87. And it's actually a very famous radio source. It's hard to see, but this little jet is actually a jet that's coming off of the black hole, the central black hole of M87. More on that in a few minutes. Now, let me show you another movie. This is a movie from the Sloan collaboration. And the Sloan collaboration is taking images of the sky and spectra from the sky, and it's doing it in stripes. And so those stripes are what you're seeing. We are located at the center of this image, and each one of these butterfly wings is a little strip of 10 degrees or so on the sky that ranges plus or minus 90 degrees. And the survey is filling in a solid angle, but it's actually easier to display it in strips because it's hard to visualize things in 3 dimensions on a 2-dimensional screen. So, and here the galaxies are just put in through artwork. You have spiral galaxies in blue, you have those elliptical galaxies in red. And as we move out, you'll notice that, again, the distribution is not random. The distribution is highly structured. There are voids, there are filaments, and at the intersection of these filaments, there are great clusters of galaxies like these systems over here. This is a billion light-year sphere that's being superposed now on the distribution. And here, this is our kind of local cosmic neighborhood. It's, again, within a billion light years. And what we're doing in this modern age, in the 21st century, is expanding our view to encompass essentially the entire visible universe. And that's what we're going to end up with here. The red dots that have just been superposed are what are called large red galaxies. Astronomers like to label things, and sometimes they label things with a very obvious term. Large red galaxies you can see to greater distances. And as we move out, you'll see that the distribution becomes more uniform looking because the scale at which structure happens is actually smaller. These structures are still not yet amplified greatly. And finally, those white points were quasars in the Sloan Digital Sky Survey sample. Quasars are galaxies that are having a very active point in their lives, strong emission from their cores. And now we're going to back out all the way, and this little bubble that we've put around here is the cosmic microwave background radiation. It's at a different wavelength. It's at radio wavelengths, but the color coding is for temperature of the microwave background, photons that are seen. And this is basically tens of billions of light years across. This has the dimensions of the entire visible universe. So we're living at a time when we can make a picture of the entire visible universe, and over our lifetimes, the surveys will fill out this volume, and we will have essentially a complete map of structure in the cosmos. Okay, so let me summarize for you. Our Milky Way galaxy is part of a local group. Here's another image of that local group. Our Milky Way is here. We have a collection of small galaxies around us. Andromeda and its collection of small galaxies are there. In a few billion years, we'll merge and create a small group. And in fact, the Milky Way and Andromeda will merge to create an elliptical galaxy. And then that group lies on the outskirts of the Virgo cluster, and that Virgo cluster is embedded in this large-scale filamentary network. So that's where we are. What about what we are? And here it's, I should say you'll learn more about this, obviously, from Sam Ting when he comes in his talk. But it's the triumph of 20th century physics that we understand very well an atomistic description of matter and energy in the universe. And it basically can be summarized in this chart. And if you do what the ancient Greeks wanted you to do, keep breaking up, take a piece of wood, break it up, 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 keep going down, 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 ultimately you get to atoms which have electrons surrounding nuclei made out of quarks. And all of this stuff that's in the room right now is made up and down quarks and electrons. And there are neutrinos streaming around, but they don't do much. They don't interact very much. It turns out for some reason that nature provided us not just with this, but with replicas, 2 other higher mass versions of the same set of particles. And they exist, they exist, but they only for short periods of time. They're short-lived. So they're not stable enough to build bodies that will be around for 100 years, let alone 10 to the 10 years. And these things interact via forces that are mediated by another set of particles that are called the vector bosons. Sam Ting will tell you more about that, as will probably Sarah Cremonini, who is actually here this morning. But there's lots of questions. Why free families? Why do we get these replications? Why the different forces? And then is that all? Is this all we get? And probably the answer is no, because remember, if I were giving this talk 100 years ago, that whole diagram didn't exist, right? We didn't know about quarks until the 60s. And so we're continuously probing and defining new particles, new fields. So there's no reason why we're done, to think that we're done. And in fact, many physicists, including our own Gordy Kane, believe that there's another piece of the world out there that's kind of hidden from view right now. And it's a supersymmetric part of the world, and there's a whole set of particles associated with that supersymmetric part of the world that we'll discover, hopefully, with the upcoming Large Hadron Collider that will turn on soon. But that's another talk. That's not going to be my talk. But in fact, underneath all of this is, of course, potentially string theory. And Sarah will talk about that next week and the week after. But the existence of these extra particles allows for the solution to a cosmic mystery that has been around since the 1930s. And that cosmic mystery is dark matter. We know that we need dark matter because of the work of people like Vera Rubin, who in the 1970s went out and took some measurements of what are called rotation curves of spiral galaxies. So here is a spiral galaxy, NGC 6503. What you do is, this spiral galaxy is like a pizza crust when you flip it up in the air and it's rotating around. And you can measure the rotation speed and plot it up. Here's that rotation speed plotted as a function of distance away from the center. The stars, as you see, kind of die away. The stars and the gas die away as a function of distance from the center. And so if that's all there was, you'd expect the rotation speed to go up, but as the amount of mass goes down, so the speed should drop. But we don't see that. What we see are the data points shown with the error bars, and the velocity goes up and it stays flat. And it stays flat because there's extra mass in the galaxy. This whole thing is embedded in a halo, and that halo actually stretches to about the size of the front wall here. Okay, so it's really nestled in to a little nest. It's like the mothership of dark matter. And our galaxy lives in its halo of dark matter too. How do we know dark matter exists? There's other ways. General relativity says that mass bends space, right? It curves space-time. And you can see that curvature. It acts like a lens. And you can see it when you look at a great cluster of galaxies. So here's a cluster of galaxies, Abell 1689. All of the yellow blobs in there are galaxies in the cluster. But the blue blobs, which are maybe a little hard to see, and I'm going to focus up in a second on them, are behind the cluster. And if the cluster acts as a lens, then the light from those background galaxies will get distorted. And in fact, you can see some distortions. Maybe you can see up here, over here. But let me blow them up. Oh, and there'll be more on clusters from Eleanor Rozia's talk on the 8th of March. But here's some images of the distortions. Gravity doesn't like to make lines. Gravity is a 1/r² force. It's a spherically symmetric force. It's very hard to sustain a linear system with gravity. So, gravity doesn't want to make a system that looks like that. It's not stable. It's unstable. But that's an apparition. The system is really a galaxy that's like any other galaxies, a spiral or a disk. But it's an illusion. It's being seen through a lens, and that lens distorts the image. From the amount of distortion, you can measure the amount of matter that needs to be there. And in fact, we get the same answer that comes out of the rotation curves. And I'll quantify that answer in a few minutes. Okay, I want to switch gears back to the microwave sky again. And that's going to lead, I only have one demonstration today, so we're going to do the demonstration. But before we do the demonstration, here, let me familiarize yourself. If you could see radiation with a wavelength around the size of your pinky, and you stared up at the sky, what you would see is this. You would see a uniform distribution of radiation. Boring, perfectly boring. If you could then look more carefully and blow that and remove the mean image and amplify the deviations around the mean by a factor of 1,000, you would see this. And that is, you see, and I should say let me orient you. This is the sky, entire 4 pi of sky mapped onto a 2-dimensional piece of paper in the following way. If you look to the center of the galaxy, it's right here. the north pole of the galaxy is the top, the south pole of the galaxy is the bottom, and then you just have to start somewhere and wrap around to go from there to there. Okay? So this is the whole sky. It's a way of projecting the sky, an ATOF projection onto a two-dimensional piece of paper. And this signature is a dipole signature. It basically says we're heading in that direction, we're moving that way, and moving away from that direction. And so when you move toward a uniform sea of radiation, it appears hotter. This is relativity that our students do in their junior and senior years. And when you move away, you see a cold spot. So there's a hot spot and a cold spot. That's just where our galaxy is moving. So let's subtract that away. We can subtract that away. And what you see are these images. First, you see the Milky Way disk. And now we can model out the disk, and what we see is essentially remnants of some fluctuations on the sky. And in the case of COBE, those satellite images, COBE provided us with essentially the first evidence for the origins of us. There was noise. This map is really mostly instrumental noise, but there was excess noise above that required by the instrument. And that led us to say, gee, there were really small variations in the constituency of the universe when the universe was about 400,000 years old, which is when this radiation was released. Okay, and what I'm going to show you in the next few slides is where we've come since then. And to give you a handle, I'm going to show you a spectrum. I'm going to show you a power spectrum. I'm going to show you an angular power spectrum. And so in order to give you a sense of what an angular power spectrum is telling you, I would like to call upon the service. We have a demonstration, and I'd like to call upon the services of my daughter, Ray. And my daughter, Ray, is a junior at Pioneer High School here. And in fact, she is getting science credit. Not extra credit on top of just arriving here. She's getting credit for participating today. So what we're going to do is we are going to just sing a scale. Okay, we're not going to sing a song for you, but we are going to sing a scale. Do, do. Okay, do. Ready? Do, re, mi, fa, sol, la, ti, do. Excellent. Thank you, Ray. Do, re, mi, fa, sol, la, ti, do. Do. Okay.
She's on top this time.
Okay, she's on, great. So let us just examine, what you're seeing here is you're seeing the amplitude of the sound that's coming into the microphone, and this is me and this is Ray, who didn't quite hold the microphone, as close as she could have, so she was a little softer there, but that's fine. Here's the actual waveform broken down at the level of a sort of 100th of a second, and this waveform is comprised of waves. And those waves, when you break them up into just individual sine waves, a sine wave is characterized by a frequency and an amplitude, as the students will remember from our physics class. And when we look at what we can do is we can then break up this signal into its constituent waves. And here's frequency ranging from 0 to 1,000 hertz. And this is the power, that is to say the amount of signal at each of those frequencies. And when you sing, and when you try to keep some pitch, you're generating a fundamental harmonic plus all of the harmonics on top of it. And because Ray is a young woman and I am an old man, my voice is an octave deeper than hers. And so my fundamental frequency lies here at about 120. Her fundamental frequency lies here at about 240. The bleeding of my voice into her microphone leads to my little blip showing up there, okay? But as you saw, as our pitch went up, and maybe, Emily, you could run that forward, there's a shift in frequency, right, as our pitch gets higher and higher. So essentially, the map I'm going to show you in a minute is what we're going to do on the map is the spatial analog of what we're doing with the time sequence here. Here we had a time sequence that we broke up into waves that are functions of time. On the map, we're going to break up the map into signs that are functions of angular position. That's what generates an angular power spectrum. Okay? Before we do that, let me remind you about The person who was largely responsible for much of this work in the field that's become very, very important in cosmology is David Wilkinson. David Wilkinson was a Michigan alum. He did his undergraduate work here as well as his graduate work here. And David went on to have a very, very productive career at Princeton University. And this is an obituary from Princeton University. He died in 2002, just as a satellite that we're going to see the results from was being launched and starting to take data. So it was kind of fitting that that satellite was then named after David. It became, instead of the microwave anisotropy probe, it became the Wilkinson microwave anisotropy probe, WMAP. And let me just read from you a little bit down here. According to Lyman Page, who's a very eminent researcher doing this kind of work, and also a colleague at Princeton University, he was the ideal, he being David, the ideal of a scientist on absolutely every level. He was an unparalleled statesman for science, a promoter for the field and for good science everywhere, while at the same time never promoting himself. And that, I think, is, that's what we should all aspire to. Right? All scientists should really be out there working for the good of the field and not for your own good. 2001, he was awarded the National Academy of Sciences James Craig Watson Medal for his contributions to the science of astronomy. So, Dave, here is your probe, the Wilkinson microwave anisotropy probe. This is an artist's rendition. It sits out at the L2 point, which the sun's down here, the Earth, the moon, and out here is a stable point where the thing just tracks along with the orbit of the Earth. And it will see all the sky over a few years. And in fact, that's what it did. It was able, therefore, to make this map, which is a much higher resolution version of the map from the COBE satellite that I showed you on a few slides ago. And I've taken out the galaxy. This is basically what's beyond the galaxy on here. And I think if you look with your eye, you will see things like, well, first of all, you see a big cold spot here. What's being color-coded here is the temperature of the microwave background radiation on a scale where the temperature varies by only 10 millionth of a degree Kelvin from red to blue. 10 millionth of a degree Kelvin, 10 to the minus 5 Kelvin from red to blue. Okay? That's pretty subtle variations, but they're detectable, they're measurable. And, but I think what you can also see is that there's kind of a characteristic size to these spots. It's like the universe has acne, there are spots, or chicken pox or something. And those spots have a particular size. And when you do the frequency analysis of this map, that's indeed what you see. What you see is that there's power, this is power, as a function of angular size, where angle is up here. So low L's is actually large scales, large angular scales, and high L's is small angular scales. And there's a peak at about a degree. Those little dots on that map are about a degree size. And that degree scale is very important for ways that I think maybe Dragan Hutterer will get into more detail with. But I'm not going to go into details here. Let's just say that there's a model universe in a red line that fits the data exquisitely well. And the data points have extremely small error bars. So this is an important piece of observational information telling us about the constituency of the universe, what we're made of, and what our history has been. Another important piece of the observational puzzle came about a decade ago from observations of distant supernovae. And I know that Dragan Hutterer will speak more about this in his talk about dark energy, because this is essentially how dark energy was discovered. The Accelerating Universe in 1998 was the science breakthrough of the year. And essentially, it came from data that looked like this. Here is a magnitude, the apparent brightness of supernova type, a special type of supernova that we know intrinsically have pretty much all the same brightness. So you can look at when you look at them on the sky, their apparent brightness tells you the physical distance to them. And by plotting physical distance versus redshift, you can understand the elements of the universe that are driving the dynamics of the expansion. And so what happened was that our model that we thought was true, which had this omega parameter that's a mass density all in ordinary matter, that model doesn't work. It's the dotted line. And the data prefer this model in which we have to have just a third of matter and 7/10, roughly speaking, of something else, and something else with a very, very funny equation of state, as we call it, a very funny relationship between pressure and energy density. And that's what the dark energy is. So the diagram, as I mentioned, we'll talk to you more about this in detail. Let me just summarize where we are right now in terms of this graph. This graph basically puts 3 independent observables, the clusters that I showed you earlier, and we can measure the mass density well from looking at measuring masses through gravitational lensing techniques and other techniques. The supernovae and the cosmic microwave background radiation all constrain, these ellipses show you where our universe is in this model space. And the model space consists of the amount of ordinary matter, phrased in some dimensionless form, and the amount of dark energy, also phrased in that same dimensionless form. And what you look for when you have independent constraints like this is that there better be a region where they overlap, and hopefully they all overlap in the same place, because that shows you that you are all pointing to the same answer. And they do overlap, and they overlap right here. And that overlap says that we have a matter density of about 25% and a dark energy density of about 75%. And what about us? What about the ordinary stuff we're made of? Well, it turns out that we are 4% of that total. Dark matter dominates the mass density. That 25% is about 21% dark matter and 4% ordinary matter. Okay. So here is kind of the central, we're at roughly the halfway point of my talk, actually a little farther than that. And here's what I want you to take home with. This is the main message that we've sort of got so far. Here's where we are at start of the 21st century in terms of our understanding of how things came to be in the universe. There was the dawn of time. After the dawn of time, there was a period where we expanded, where the part of the universe we live in went through this rapid expansion of space, in that era we call inflation. We currently don't fully understand how inflation fits in with say the standard model of particle physics, but that research is ongoing. That period of inflation basically took our patch of the universe and just greatly expanded it, but at the same time, because that was all happening when essentially all of us in the room and everything in our observable universe was on the atomic scale or smaller, then quantum mechanics really drove the dynamics of the system. And what you know, if you know anything about quantum mechanics, what you know is that it's uncertain in the sense that it's a probabilistic theory. It's not uncertain in terms of it can't make predictions. You can make predictions, but those predictions are always in the form of probability densities. And that's Heisenberg's uncertainty principle. That's at the core. And so that provides us a mechanism then for introducing fluctuations in the energy density. Because it was a quantum system, it's not going to be exactly homogeneous. One place is going to be a little off kilter with respect to the other. And that's good, because we wouldn't be here if that didn't happen. We'd be in a boring universe filled with hydrogen that was completely uniform, filling space. That's boring. Okay, that inflation happened. Then at about 380,000 years, the photons stopped interacting with electrons and protons because those electrons and protons were able to recombine to form neutral hydrogen. And photons will just kind of ignore neutral hydrogen. And that's why in the microwave sky, what we're seeing are these 14 billion-year-old photons that have just traveled unimpeded, largely, into our telescopes. And then in that intervening period of 14 billion years or so, we took the small fluctuations that are there at the level of 1 part in 100,000, and gravity amplified them to create the structures that we see today. And the nice thing about this part is that it's classical, right? That is to say, that's the machinery part of the adventitious machinery. We can now take a standard Newtonian perspective and model the development of structure in a classical way from just this period up until the present. And so but the point is, the take-home message is, we are amplified noise. That's the central theme. But let's focus now on going to our computer and putting the universe into a computer, okay? And I like this far side. My computer doesn't come with a smart key, which is probably a good thing. Okay, so here's where I'm going to get a little off topic in the sense of I want to just introduce to you, what's really happening. We have Google in town. Welcome to any of you folks who are working there. And what's happening is we're able to capture a lot of events and store them digitally and then mine them, and that's essentially what search is all about. I mean, when you think of search, you think about, okay, I need tickets to the game or something like that, But search goes deeper than that. Search is connecting different communities that are interested in very different things, but there's a thread that connects them, and you want to make that thread happen. And in previous parts of history, it was hard to do that. Now it's becoming much simpler. And so let me just say that Einstein gave us the notion of events, space-time events, and that was the way to build your model of space-time. But the space-time was kind of empty, right? It was just positions and time. I mean, it was just a way of labeling space and time. But that's a kind of boring universe in the sense that what the picture was one of kind of inert observers who just send each other light signals. When in reality, what we know is that space and time are filled with things, and those things have attributes. And the things that you care about depend on your perspective. They depend on your sense of scale, if you will. All right, so for me, I actually work on the kind of scale of the universe, and I care about things called clusters of galaxies, and the attributes I label those systems with are things like how many galaxies do they have, how much dark matter do they have, what's the leftover gas that shines in X-rays in them, et cetera, et cetera. But then I have friends who work in extragalactic astronomy, and those guys want to take one of my galaxies and say, hey, I want to look inside of that system. And so you look inside of that system and you identify stars and planets and other things. And then you go over to the geology department or biology and chemistry departments, and you start talking to people who work in planetary science who are thinking about life. And is it a carbon-based form? Is it silicon? Is it something, whatever? And then get to the species level, and then you can talk about society, and you can talk about humans, and you can talk about things like age and income and desires. You can put attributes on us, right? We all have attributes, and what's happening now is those attributes are increasingly becoming quantitative, right? You think that love is, a property that's going to be hard to quantify. Well, people are out there trying to do that. Right? You know that, and apparently, so one thing I read this past week, which I don't know if it's true yet, but 20% of the marriages in this country apparently have their roots in, is it Match.com? One of the online match services apparently claims they're responsible for 20% of the marriages in this country in the last year. That I find amazing, right? Let me give you an example of in our physics department, the complex systems program has a talk on Thursday. And if all of you show up, I think we're going to be in trouble. But if you're free Thursday at 1 o'clock, there's a talk in West Hall by an associate professor in political science at UCSD on the dynamic spread of happiness in a large-scale social network. Watching happiness spread, measuring happiness spread. That's what he's doing. He's looking at 5,019 individuals over 18 years in the Framingham Heart Study social network, which is published data. It's on the web. He browsed, pulled it down, and started doing cluster analysis on it. Clusters of happy and unhappy people are visible in the network, and the effects of one person's happiness appears to extend up to 3 degrees of separation to one's friends, friends, friends. And then, moreover, network characteristics predict which individuals will be happy in the future, particularly those who are surrounded by many happy people, duh. Sorry. And those who are highly central in their local networks. So the science of happiness is upon us. Let me show you another example. This is stuff that I've worked on several years ago with Mark Newman in our department and Kirby Shedden in statistics. Mark Newman is a member of the complex systems group here and was our first hire in that area, in fact. And what we did was we took all the introductory level enrollments for a 4-year period in the College of LS&A, the Literature, Science, and Arts, and we made a measurement of co-enrollments between courses in the 100 level categorized by department, okay? And then we created this network which shows you sort of the proximity of one department to another as measured by the excess over random enrollment. You're looking for excess over random. So you measure that, and then you connect up departments by that measure of excess over random co-enrollment. And here's the picture, and the colors aren't showing up all that well, but blue is natural science, yellow is humanities, and green are social sciences. And in some level, the placement here is on the page is somewhat random, except if you're central, that's important, and if you're on the periphery, that's also important. So when you look, you see some central departments are psychology, anthropology, English literature. Well, that's not surprising. Everybody has to take an English class. They have to do English 125 or place out of it. So, that's what makes English Lit be part of the central part. This is 100 level classes, remember, introductory classes. There's also a language requirement, which is why Romance languages, and many people take Spanish, or French. And so one of the Romance languages sit in here. And anthropology and psychology are just, very core parts of our curriculum here. They're very strong departments. They historically have been very strong, along with political science. And then you see that physics and chemistry kind of live out here on the periphery because we kind of, engineering isn't on here. And we have, we stretch out to engineering. So we get kind of pulled off, if you like, because of that. But on the other hand, astronomy lives in here because all of the freshmen and sophomore have to satisfy a natural science requirement. And a lot of the ways that the most popular way to do that is by taking an astronomy course or a geology course. So that's why they live down here, closer to the root of the college. So that's the 100 level view, the introductory level view. Let's go to the 300 level courses, which are advanced. And the picture changes pretty dramatically. What you see is now a cluster of green, a cluster of yellow, and largely a cluster of blue, with the exception of statistics, because statistics has this course 350, which is actually a 100 level course, and it really needs to be renumbered. And so, Dean, if you're watching, fix it. But anyway, and this is a measure of how it is. It's just this weird. So that's why they live over here. But you have your natural science folks, and what's interesting is that astronomy, physics, and math cluster together, and then the biological sciences also kind of cluster together, and geology is a little unclear exactly. There's a lot of chemistry in biology, right? A lot of that. So, and then you basically have these majors that emerge. You can now see why we have a natural science. Why we break up the college into or why we think about the college in terms of these divisions. Okay, so let me get back to physics. I'm going to show you a little bit of simulation work, and then end on and come close to ending, hopefully on time. So when you try to do in silico representations of our physical universe, you're basically working on the following set of assumptions. You're believing that the laws of physics as we know them and test them here have applied over all time and throughout all space. Also, we're assuming that general relativity, or gravity, is what's driving the evolution of the universe on its largest scales. And then for systems that emerge within the universe, within our visible universe on small scales, we have complex processes that happen, chemical processes, radiative processes, et cetera, that produce the rich phenomenology that we see in astrophysics, chemistry, biology, society, et cetera. So what part of it, let me just show you the gravity part. Here's a set of images from a good friend and colleague of mine, Volker Springel, a part of the Virgo consortium. This is a box that's 300 million light years on a side. What we're visualizing here is the dark matter density in that box, where bright spots have high density and dark spots have low density. So in the early stages, this box is about 500 million years old. This is 2 billion years, and this is 14 billion years today. And so you go from a very relatively smooth distribution to becoming increasingly clustered, and you develop this filamentary topology that we see in the galaxy distribution today. Now you can quantify that, and I'm not going to show you the specific measurements, but you can do correlation functions, power spectra analysis. There's all sorts of real, honest labor and statistics behind here, but I'm just going to show you a map, okay? Because you can visually do your own power spectrum in your head that way. And the blue, this part up here, are real, honest galaxy surveys. The red part down here are mock galaxy surveys, artificial galaxy surveys generated through these computer simulations. And I think when you look at this, you'll say, statistically speaking, I mean, we're not after putting the Milky Way galaxy exactly where we are, because we don't even know where, where's here in our in silico representation. There is no here, okay? But you could pick out a galaxy that looks like ours. There's plenty of spiral systems or galaxies of the right size that you could choose. And in fact, that's what's done in making these maps. We choose a local region that looks like our local group so that we can get a perspective that looks more like our local group. And there's pretty good, actually very good, fidelity in the simulations today. However, when you get down to very small scales and you start looking at that rich phenomenology of the astrophysics, things are getting a little more complicated, because here's a Hubble Space Telescope collection of a bunch of galaxies. And you see there's a lot of morphological variation. On the other hand, there's similarities. You see galaxies that look pretty normal, like our Milky Way. But look at this guy. This guy, it turns out, is a system. It can be explained by an interaction where there's a satellite galaxy that plunges directly through the core of a galaxy, and that core creates a pulse of stars, and that pulse of stars goes out radially. And in fact, that little donut ring of stars is the leftovers of this collision. Okay? And it's not going to be there in about a half a billion years, but we're not going to wait around. If we're still around in a half a billion years, we'll be able to demonstrate that really is what's happening there. So how do we model that? Well, that's really complicated. Here's kind of a sketch. If you want to become a galactic engineer and build computer models of galaxies, here's the flow chart. You put in some quantum noise to start. You amplify it by gravity. But then you've got to take the dark matter, let it cluster, because the dark matter doesn't interact with radiation. That's weakly interacting. But the baryons, the stuff we're made of and the stuff that swarms the stars, interacts with photons, with radiation, like crazy. So you got to put all that interaction in there. And you got to put in the process of nuclear fusion, forming stars. You got to put in the process of stars blowing up, becoming supernovae. You got to put in the process of black hole creation and accretion disks around the black hole to turn on quasars. You got to put all that in. All that stuff is hard, I'll tell you. So I'm putting it up here as a black box, okay? But the black box over time is getting grayer, okay? I mean, it's getting whiter. Let me just show you where we stand today in terms of, here's another movie from my friend Volker Springel. And what you're seeing are two galaxies that are colliding. And you're seeing only the gas in those galaxies, okay? Imagine there's stars and dark matter as well, but we're not showing them to you. We're just showing you the gas. So the edges, and it's colored by temperature. So red is hot. When their edges touch, the gas gets compressed and shocked and heated up. Some of it gets torn off. The gravitational interaction is throwing off these tidal tails as they swing around one another. And they're bound. The total energy of the system to start with was negative, so they're destined to ultimately merge. And now what you're seeing is venting. That venting is because Volker has put in a central black hole into it. He's put in the existence of a central black hole into these galaxies. And he's put in a sort of subgrid model, as we call it, that says when gas gets down to my central resolution element and starts feeding the black hole, I'm going to send some fraction of it back out in energy. Okay? And that's what happens. And essentially what you saw, the big collision which happened while I was turned that way, was again feeding that monster black hole in the center of the galaxy. That monster black hole says, take that, galaxy, and feeds back, right? And now the process of how that happens is not completely understood, but we're getting there. This is the front lines of research in computational cosmology today. Now, how do we know that black holes exist? Let me just show you a couple of pictures. Here is, there's the man in black. Here is a galaxy, I forget its NGC number, but this is an image from the Very Large Array radio telescope. And the size scale, this galaxy is sending out jets of energized particles that then create radio waves through interaction with magnetic fields. And the size scale to which this material is being thrown is about 100 times the size of the galaxy itself. Is enormously energetic. And the only way to get that kind of energy that we know of is by falling into a very, very, very deep gravitational potential well that is a black hole, and taking some of that energy and using it to create a big pump that exerts this jet. And here is a nice image of two cores of two galaxies that are colliding. And actually, the thought is that these jets are actually representative of material being thrown out from black holes in the centers of each of those galaxies. And I think maybe Larry Jones will. So energetic particles come out of these regions, and that's part of the cosmic ray budget in our galaxy is because of interactions like that with the black hole. Okay, so where are we heading next? We're heading into era of very large surveys. And Michigan is part of a very large upcoming survey called the Dark Energy Survey. And that is an NSF and DOE jointly funded project that will image a large chunk of the southern sky, about a quarter of the southern sky, to a depth that's about a factor 10 deeper than current surveys. And we're going to study dark energy using 4 techniques, and I think that Dagan Huderer will probably get into this in detail. But it's a modest-sized project by DOE standards. It's a few $100 million budget. It will run from, construction is happening now. The survey will kick in about 2011, and will run for 5 years, and will consume about a third of the telescope time at this telescope, the Blanco telescope in Chile. This is a Southern Hemisphere survey. In addition to that work, there's also projects that are very long time scale but happening. This is things like the James Webb Space Telescope, the successor to the Hubble Space Telescope, which will have far better infrared sensitivity than Hubble, as well as larger collecting area. And that will enable it to peer very, very deeply into the universe. Because of the red shifting effect, you want to go red, and it will be able essentially to see the first star clusters that turn on in the universe. That's the goal of one of the goals of James Webb Telescope. There are big questions left. Why do we live in a 4-dimensional spacetime? What is the vacuum? What lies beyond our light horizon? Et cetera, et cetera. Let me just bring in Lord Martin Rees, Astronomer Royal of Britain. And a friend of the family, as it were, at some level. But I interacted with Lord Martin at Cambridge when I was there, and he's really a fantastic guy, and he's visited campus several times over the past few years. And he is one person who thinks that, why not? Why can't we have more than one universe? And why aren't the local laws of our local patch just kind of local bylaws? So there could be other universes out there. Another person who's thought about this is Paul Davies, who has come to visit here, and I grabbed a slide from him. And the idea is there's some kind of standard model parameter fixer that makes the Big Bang happen. And it happens in our universe, but in other universes, and we just happen to land in this domain. Who knows? The thing is, when you see this phrase like standard model parameter fixer, that's pretty anthropomorphic. So is this what we think of as God? The issue of God intersecting with science has been in the popular press quite a bit recently, and I think that the spectrum of discourse, if you will, on this is kind of defined by maybe Francis Collins, who's a former professor here, who was head of the Genome Project. And on one extreme, and he wrote a book that was published last year called The Language of God, A Scientist Presents Evidence for Belief. And on the other extreme, you have Richard Dawkins, who appeared on South Park in caricature. I don't know how many of you in the audience will have seen that episode, but I suspect maybe there's a couple of them. And he wrote this book recently called The God Delusion. And if you go to his website, he is claimed to be the world's most prominent atheist, which I'm not sure is, it's a pretty bold statement to make. My own personal journey has kind of taken me from age 8 on this side to age 48. It's closer to this side. I'm still, I think, somewhere in the middle. But what I care is not about this issue is not important. Before we get there, you might argue that my journey is because of the fact that, I had a kind of hardscrabble existence. Now that I'm a professor at the University of Michigan, I make a decent living. Maybe it's just that I got less religious as I got more affluent. And you can ask this question, the Pew, I forget what, the Pew Research Consortium, whatever they're called, analyzed this on a national scale, and they measured, again, this is like the happiness measure. There's a score of religiosity. You can quiz people about how religious they are and turn it into a number. So they do that. And then you can pretty easily, turn your monetary income into a number. And so take the GDP of a country, which is down here, the gross domestic product, and plot it against this score on religiosity. And there is this kind of anti-correlation. That is to say, African countries, which are still developing countries, tend to be fairly religious. Whereas the more affluent, Western Europe in particular countries are the lowest on the religiosity scale. But what I find really intriguing is look where the US ended up. The US and Kuwait are the outliers here. And the Kuwait, right? And Kuwait, you would argue, is an outlier in this direction, right? Because of oil. Whereas the US is not an outlier in that direction. The US is an outlier in the vertical direction, right? So what I think about this issue is not important. What you think about this issue is what I'm interested to know. So your last question for today, which is by far the hardest question that I've asked you, is the following. I want you to tell me all your thoughts on God, but at some level, but I'm asking a very specific question here. And unlike the other questions, I will not post the correct answer after this question. That's why the anonymity, so that shows you that the anonymity that's provided by these clickers is actually important, because students, rather than raising their hands, students can provide answers that don't point back to them as to being the source of the answer. Okay, what do we got? Oh, now here's where you let me off the hook, because my students like it for me to predict what the correct response rate is going to be in advance. And so you could have asked me what I would have thought my your answers would be in advance. And I think I would have chosen the peak to be here, not here. Now, that's intriguing. Okay, well, good. Emily, if I could have my display back, let me just remind you what one of the prominent astrophysicists of the 20th century said on this issue, and it comes down to essentially first cause. If you want to kind of put God there as the Big Bang model fixer, here's the words of Carl Sagan in this lovely book, which I urge you to pick up. It's sitting at Borders. There's a whole bunch of them there. This was actually a series of lectures he gave at University of Glasgow, and the remarkable thing about this book is it's the transcription of his lectures, but you read the book, and the man speaks in complete paragraphs. The man could write a book by dictation, pure dictation, start to finish, done. Astounding. Anyway, there are two conflicting hypotheses here, two alternative hypotheses. One is that the universe was always here. The other is that God was always here. Why is it immediately obvious that one of those is more likely than the other? Or put another way, if we say that God made the universe, it is reasonable then to ask, and who made God? Which is what, in Catholic school, you did that in 3rd grade and you were shushed. No, that's not entirely true. Accidents happen. This is an image where two galaxies are nearly the same redshift, but they're projected on one another, right? There's one galaxy this looks like a funny galaxy, but it's actually two that are projected one on top of each other. Here's a gravitational lens, another accident. This is actually, if we've had the lights down, this is a pair of gravitational lenses where 3 galaxies are lined up on a line at a level of precision that's ridiculous. They're lined up at the scale of one or a few arc minutes on the sky. That's 1 part in 10 to the minus 6 in angle. So 1 millionth, and another 1 millionth behind it. That's very remarkable. So I'll leave you then with my final message. We may be amplified noise, but just as the history of jazz music in the 50s, there were some greats, John Coltrane, Ornette Coleman, Miles Davis, who at some point in their career, and in the case of Ornette Coleman, probably his entire career, were making music that sounded a lot like noise to people. So my hope is that the noise that we have today will be tomorrow's music. Thank you very much for coming.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.